Welcome to this lecture on trigonometric functions. Today, we are going to look at sine and cosine in a completely new way. Instead of using triangles and circles, we will build these functions from scratch using infinite polynomials. This is a foundational concept in advanced calculus that powers modern computing. Now that we have introduced our topic, let us understand how we can build a wave. Imagine trying to build a smooth, repeating roller coaster track using only straight and slightly curved pieces of wood. A single piece will not look like a wave. But if you glue an infinite number of these simple polynomial pieces together, bending them just right, you create a perfect wave. In advanced mathematics, we define sine and cosine strictly through these infinite sums called power series rather than geometric ratios. Building on that idea, let us look at the exact mathematical recipe for the sine wave. Conceptually, this formula glues together odd powers of our input variable to shape the curve. The symbol x represents the input angle, which must be measured in radians, not degrees. The exclamation mark is the factorial operation, meaning you multiply the number by all whole numbers below it. As the input x increases, the higher powers grow large, but the factorials in the denominators grow much faster, keeping the wave perfectly stable and finite. Just as we built the sine wave, we can construct the cosine wave using a very similar formula. The cosine function is built using only the even powers of x. Notice that the very first term is the number 1, which corresponds to x raised to the power of 0. The signs alternate between positive and negative, just like the sine series. Because the factorial denominators grow incredibly fast, this series converges for any real number. This means you can plug absolutely any value of x into this formula and safely calculate a meaningful result. Before we move on to calculations, let us see this with a concrete visual example. This diagram beautifully illustrates how these simple algebraic building blocks stack together to form a wave. The solid blue line is the true sine wave. The straight orange line is just the very first term of the series, y equals x. As we add the cubic term, shown in green, the ends bend down to hug the true wave. Adding the quintic term, in purple, makes it hug the wave even further out. This is exactly what a power series does behind the scenes. Now that we have seen the visual, let us use the formula to calculate a familiar value. We want to find the exact value of sine at the origin, using only its formal power series definition. We substitute the value 0 directly into the infinite sum. Because every single term in this infinite series contains a power of 0, every term evaluates to exactly 0. There is no constant term standing alone. Therefore, the entire infinite sum collapses to nothing. This confirms the familiar geometric fact that the sine of 0 is exactly 0. Following the exact same logic, let us evaluate the cosine function at 0. We substitute 0 into the cosine power series. We must pay close attention to the very first term of this series. The first term is the number 1, which does not have an x attached to it. All the subsequent terms contain powers of 0, meaning they will all vanish completely. The infinite tail contributes absolutely nothing. This leaves us with just the constant term, proving that the cosine of 0 is exactly 1, perfectly matching our geometric understanding. Having evaluated exact values, let us see how these series are used to approximate values that are difficult to compute by hand. We want to find an approximate numerical value for the sine of 0.1 radians without using a calculator. Because 0.1 is a very small number, raising it to higher powers results in incredibly tiny fractions, so we can safely ignore later terms. We truncate the series, keeping only the linear and cubic terms. We substitute 0.1 and expand 3 factorial to 6. This sets up our calculation. Continuing our calculation, we now evaluate the cube of 0.1, which gives us 0.001. We divide this tiny decimal by 6 to find the value of our second term, yielding approximately 0.00016667. Finally, we subtract this tiny correction factor from our initial value of 0.1. This gives us a highly accurate approximation. If you type this into a scientific calculator, you get a nearly identical result, proving that just two terms can do the heavy lifting of complex trigonometry. Now that we have used these formulas for calculations, let us prove a fundamental property of calculus, the derivative of the sine function. Instead of using complicated geometric limits, we will prove this purely by differentiating the power series term by term. We begin by writing out the formal definition of the sine function as an infinite sum. Next, we apply the derivative operator to both sides. A powerful theorem allows us to pass the derivative inside the infinite sum, treating it just like a very long, ordinary polynomial. This sets up our differentiation. Continuing our proof, we apply the basic power rule to every single term. The derivative of x becomes 1. For the higher powers, the old exponent drops down as a multiplier in the numerator, while the new exponent is 1 less than before. The factorial denominators remain completely unchanged during this step. To simplify these fractions, we expand the factorials in the denominators just a little bit. For example, we rewrite 3 factorial as 3 times 2 factorial. We do this specifically to expose a number in the denominator that matches the new multiplier in the numerator. In this final step of our derivation, we cancel the matching numbers in the top and bottom of each fraction. This clever algebraic trick leaves us with a brand new infinite series. Notice that this new series contains only the even powers of x, starting with the constant 1, and the denominators are the factorials of these new even powers. If we look closely, we recognize this immediately as the exact formal definition of the cosine power series. Therefore, we have rigorously proven that the rate of change of the sine wave is perfectly described by the cosine wave. So, we have proven that the derivative of sine is cosine using series. This brings us to an important question. Why go through the trouble of redefining familiar shapes using infinite sums? The primary reason is that computers and calculators do not have tiny protractors inside them to measure physical angles. They only possess microchips capable of performing basic arithmetic like addition and multiplication. By defining trigonometric functions as power series, we translate complex geometry into simple arithmetic that a machine can process. Furthermore, this allows us to plug in complex numbers, which is absolutely essential in quantum physics. To wrap up our lecture, let us review the key takeaways. First, in advanced mathematics, trigonometric functions are fundamentally defined as infinite power series rather than geometric ratios. Second, the sine function is constructed using alternating odd powers, while the cosine function is built using alternating even powers. Finally, this powerful analytical perspective allows us to prove calculus properties easily and compute precise values using only basic arithmetic. You have now seen how power series bridge the gap between abstract geometry and the practical computations that drive modern technology. Thank you for watching.